You can start, sir.
Okay, great. Thanks, Agar. Hi, good morning, everyone. Nice to see you back. So yesterday's lecture was, we talked about what we exactly mean by radio window, especially like the frequency range, some of the specialities that it has, right? And then we also went through some of the historical aspects of it, that how actually radio astronomy started, and that story itself is very interesting when we from a very general perspective of how we plan experiments and how actually sometimes experiments allow us to develop new theories and vice versa, right? And that's something which is very good to know and also keep in mind at the same time, uh, as we progress, as we develop our own research methodologies. Now, and then we went on to talk about like what are some of the big discoveries that have been made through radio astronomy exclusively over last 70 years, and the kind of impact they have had over not just astrophysics, cosmology, but broader understanding of the universe as well. So now today's lecture is going to be a little bit more cool radio astronomy techniques you can think of, because we are going to now focus more on the techniques through which radio signals are detected. So there are basically three main themes that we will cover today. One will be the detection of radio signals, and then we will touch upon some of the things, some of the aspects of Fourier optics, right? Because that would allow you to make a very nice connection between some of the experiments that you have done in your laboratories already, or some of the optics principles that you have studied primarily from the ray optics point of view. But I'm sure all of you have done at least 3 times Fourier transforms. You have learned them. So it will allow you to now make a connection with how you can actually use that understanding, the mathematical formulation of Fourier transforms, to understand some of your uh, optics experiments. And then we will make a direct contact with radio interferometry techniques and principles, right? What is it that allows us to build a radio interferometer like this? Yesterday, as we were talking about that, I was telling you that in your screen, you see one telescope. This is giant meter radio telescope, but it consists of 30 dishes, right? So one of the main objectives of today's lecture, you can think of it is to understand that what is it that allows us to make one telescope using these multiple elements, right? And what is it that allows us to do that? That's one thing. And second thing is that how is it that we make images of the sky using it? So imaging per se will be part of tomorrow's lecture, but today at the end of it, I think we should probably will get reasonably convinced that okay, this is something which is believable and something that we understand, right? So let us start with radio wave detection. So in radio astronomy as well as in telecommunications, the simplest of antenna or the detection technique that is involved is using dipole antenna. It's the simplest and most widely used class of antenna. It also has an additional advantage that from a theoretical point of view, we can actually understand derive its power pattern and understand it very easily. So it's something which is very good to start with, and that's something some of you would have already done as part of your electrodynamics, especially in master's level courses. And this was something which Hertz in his experiment also used when he first demonstrated the existence of radio waves. That was way back in 1887. And so he used a dipole antenna as part of his experiment, which consists of conductors of equal length, right, oriented end to end, as you can see it in your slide. And there is a then feed line which connects these two conductors. So now the fundamental resonance of a thin linear conductor like this would occur at a frequency whose wavelength is twice the wire's length, right? That's the important thing to bear in mind. So if you have a half wave dipole antenna, it would then consist of 2/4 wavelength conductors placed end to end, and for a total length of approximately, which will be lambda by 2 then, right? So this is where this term half wave dipole antenna comes through. And in this case, what would happen that your current distribution would be a standing wave, and it will be approximately sinusoidal along the length of the dipole, right, with a node at each end. Now, if I go to next slide, here you can see what would be the kind of radiation pattern of this such a half wave dipole antenna will be. By radiation pattern, I will mean that like if we use it as a transmitter, it would emit radiation in with this pattern, and if I'm using it as a receptor, then it would sort of be responsive to receiving radiation in that distribution, basically, right? So if you look at this radiation pattern here, the response is maximum perpendicular to the conductor. But then as you go away towards the axial direction, it falls to 0. So it can actually be implemented as an omnidirectional antenna if we install it vertically. And in 3 dimensions, it's a little bit more easier to visualize here. You can see that the sine square theta dependence is directivity actually looks like a toroid or a donut perpendicular to the dipole's axis. So one thing that you can easily visualize is that it's a very weakly directional antenna, especially if we use it in a horizontal sense, right? Which means weakly directional dependence means that if I point it towards the sky, it will actually receive signal from an almost entire sky, right? And for communication purposes, it can be not necessarily a bad thing, but for astronomy, as we will see, and we'll discuss in a little bit more detail, that this is something which is not a very good thing necessarily, right? So from the astronomy perspective, as we are talking about here, so a dipole may not be a very good antenna to start with, but what does it mean actually? Because then the next question that you would straight away ask is, but then tell us what is the good antenna. So let's talk about it a little bit more precise manner. And when we are talking about good antennas for in general actually, but in astronomy, we are talking about basically 2 quantities or 2 properties. One is gain and another is directivity, right? So what is gain? Gain is represents the sensitivity of the antenna, that its ability to detect fainter signals, right? And directivity represents it's our ability to tell that the signal is coming from a particular direction or not. Okay, so you can straight away understand that if, in astronomy we are interested in detecting fainter signals. We would definitely like to have antennas which have very high gain. And then at the same time, we would like to also know from which source this signal is coming from, because if you look at the sky, in the Milky Way, there will be like so many stars. If you point away from the Milky Way, you will be looking at so many galaxies, like a very small region of the sky. And if you are unable to tell that from which astrophysical source a particular signal is coming, then your ability to understand what that signal represents in terms of physical processes or what is going on inside a particular astrophysical object is very, very limited, right? You cannot really do much with that signal beyond a point, except the fact that, oh, I detect something there, right? And astronomy has long ago moved well beyond that level. So on the left-hand side of this slide, you can see a representative power pattern of an antenna, right? So this is how typically an antenna response would be, that at the center here it would have the maximum response, but that's not it. It will also have what we call as side lobes here, right? So if there happens to be a radiative source along this direction, an antenna would also receive a signal from that, and that can be a problem, right? So the first thing that we define a quantity to represent a good antenna is the beam solid angle. That's the omega A. P and theta phi here is the power pattern of the antenna, and this integral is over the entire 4 pi steradian, right? So that's the thing for you to remember. So what if I take this kind of response pattern and measure this value, what does this represent? So this is nothing but your solid angle integrated over the normalized power pattern, right? So it actually represents solid angle of an idealized antenna whose response is actually 1 inside this solid angle and is 0 outside. So such a detector does not exist. It's just a quantity that you have measured here, right? To represent the quality of this antenna. The next thing what we can define is what is called the main beam solid angle, and that's what we are always most interested in. Main beam is this, where the response is maximum here, right? So this is omega main beam. Everything is same as omega A here, except that integral now is over the main beam. So now we come to a quantity which we can use to define the efficiency of the antenna in this context, which is the main beam efficiency, and it's the ratio of omega main beam and omega A, right? So this in this case is telling me that how much of the power is concentrated in the main beam. So you can understand that the directivity of antenna would depend on how well the power is concentrated in the main beam, right? Because if, let's say, the side lobe was of same level as the main beam, then the directivity will be very poor, right? It's very easy to understand here from this directly. But at the same time, I would caution you that you must not confuse main beam efficiency as to the angular size, or because loosely it may seem resemble to you that they are fine, but it is not, right? Because here we are talking about the power that is concentrated in the main beam, and we will talk about what exactly the resolution is in this case, right? The angular extent of the main beam is generally, we will see, is defined by half power pattern beam width here. You can see it here, right? So it's the angle between the points on the main beam where the peak of the power pattern drops to half of the peak value. Okay. So now, so this is where we have now talked about one property of the antenna. Now let's talk about the sensitivity aspect of it. And before we sort of delve deeper into it, let's talk about this particular thought experiment, where what we do here is that we consider an antenna here, right? Shown here in this case here, the left-hand diagram of in the slide. So we assume that this antenna is closed by a black body at temperature T1, right? That is there. And the output terminals of this are connected to a transmission line, and they are terminated at a matched load, which is a resistor R, right? So what is the meaning of matched? It means that there are no losses, and if the transmission line and a resistor are decoupled from the outside world, then from the second law of thermodynamics, we can say that they would reach an equilibrium temperature T, right? That would be identical to the black body temperature. And furthermore, these two powers P1 and P2 are flowing back and forth to transmission line. They would be identical, right? So what we get from here is this famous Nyquist law, which says that resistor at temperature T would produce a noise power of this KT, and this is over a bandwidth of delta nu. That's why this nu subscript represents here. So this is your famous Nyquist law, not to be confused with the Nyquist rate that we come across in Fourier theory, that is or signal processing. That is something which would come to as well. That is important as well, but this is something different we are talking about here. And the origin of this power is the thermal motion of electrons, due to which, even though the mean current is zero here, as you can see, but the RMS is not, right? And due to this, what happens that this resistor provides a non-zero power input to the amplifier. And this is the basic idea of Johnson noise, right? In case you are unfamiliar with this thing, I urge you to sort of go back and read a little more about it. It's very interesting and very, very important to understand how the electrical devices operate, right? So so now the power density, or the monochromatic power that we knew that we have defined here, received by an antenna, is half A effective S nu delta nu. S nu is the flux density of the source that we are looking at. Delta nu is the bandwidth over which we are receiving the signal. And factor half is coming here because we are talking about only detecting one polarization here, right? But you can have two antennas which will be detecting both, which will be sensitive to both the polarizations, and that is something that is done with antennas. But to keep things simple here, we have got this. We're dealing with only one polarization here, and then we can equate these things, and then this is how we can relate the flux density of source to what is called the antenna temperature, right? This TA term. So this is the kind of signal my antenna is receiving if I point it to the sky. Now, straight away one can understand that the size of my detector or size of the antenna would represent actually the amount of signal that I am receiving. So this area is what I can talk about as a geometric area, which is here. But then the geometric area, we will look at it quickly in next couple of slides, is not necessarily the effective area over which I collect entire signal. And there can be multiple factors of it. Some of it will become very clear to you as we go through, talk about different kind of telescopes and antennas, right? But we then, at the same time, we can define a quantity called the eta A, which is the aperture efficiency. Okay. So the takeaway point is that collecting area determines the amplitude of antenna temperature for a given source and also the sensitivity of the telescope. So this is very much analogous to what we defined as beam efficiency, where here we define something called aperture efficiency, eta A, right? And this factor like 2K by A effective, which is coming, is gain or sensitivity of the antenna, which is we measure in terms of Kelvin per Jansky, right? Jansky is the unit in which we measure flux density, watt per meter per hertz, right? That's something which we talked about yesterday. So now the precision with which a measurement can be done, what is the precision? If I'm measuring a temperature T, then precision is delta T on top of that, right? How that is to what certainty I can tell that my signal is between T plus minus delta T or not. So that's what we mean by the precision of the signal. So while the number of measurements that we will be making will be directly proportional to delta nu, right? The bandwidth that I have and the number of samples that I collect. For example, let's say I'm collecting a signal at every 1 second, then over a minute I will have 60 signals, samples, right? So by averaging all of them, I can gain root n precision on that, right? So delta nu is the bandwidth and tau is the integration time. So the bandwidth describes the number of events per unit time, and that is multiplied by the duration of the measurement. Okay, so this is how the act of measurement takes place. Right. So now let's whatever we sort of formalize in last couple of slides. Let's try to start relating it to a real type of an antenna. So let's look at first critical aspect, which is gain. Okay. So in this case, we are talking about collecting as much power as possible. So effective area is one quantity, right? Flux density, stronger the source, more signal you will receive. Right, so as part of an experiment, we always make an assessment that okay, whether this telescope is good enough to detect this source or not, and if not, at the same time, then we try to also take into account that for how long I should integrate on the source and how much bandwidth I should use. Right, but if we are talking about just the antenna, then the detector with large collecting area is what we want. But we want large collecting area, but no stray radiation. Right, what is meant by stray radiation? That if I am looking at this source and there's another much stronger source outside of the main lobe, I do not want it to contribute much to my signal, because what would happen that this would not only confuse the signal that you're receiving, it will also raise the temperature or the noise of your system, and that is something a very undesirable thing, right? So this stray radiation you want to minimize. And the way you would do is that to identify an antenna which has a very good mean beam efficiency, the side lobe should be as minimal as possible, right? So that's the way to do it. So now we come to the second aspect, which is the directivity, which we were talking about. So directivity, you can understand in the following way. So now let's think of two sources A and B, which I'm looking through in the main lobe itself, right? So the resolution. So what is the resolution here in this case? Radiation from when I'm receiving radiation, how can I tell that whether it is from A and B? So the ability to separate out this aspect is referred to as the resolution. And a simple dipole on its own has poor directional properties. It's inadequate. for that purpose. So what we do instead is to actually, the most commonly used setup in astronomy that would you would come across is that uh, dipole is actually used as a feed in combination with the parabolic reflector, and you can understand it through this diagram here. So this is the parabolic reflector here, right here, and we will put a dipole feed here. So what happens that if there is an incoming phase front wave front from the sky, and I'm just pointed towards the sky, then the reflector will act as a large collecting surface, right? It will convert this plane wavefront into a spherical one, which means that it will get all the signal that is coming here, incident on the parabolic dish, will be collected at the focus, which is here. And since I have put a dipole feed here, it will be detected by means of this dipole antenna, right? That's what will happen. And so what is happening here, that the response at the focus is actually a result of a coherent phase summation of electric field at that's all getting focused here. But at the same time, it is nice to keep in mind that if there are wavefronts coming from other directions in the sky, for example, something like this is coming, and a wavefront is like this, then it will also actually be reflected the same way, but it will be focused at a slightly different point, right? So I can actually put another dipole feed at that another focal point where it is getting focused, and then I can detect that signal too. And that's the kind of technique which is to build what is called a focal plane array, is also used in radio astronomy. Through that, what happens that my dish, which would be sort of receiving signal only from this part of the sky, then by having this focal plane array, I can actually map a larger part of the sky simultaneously, right? So that is something which is very much done, and there are almost all single dish telescopes today use this technique. You can look at some of them, and we'll talk about some of those single dish telescopes in next few slides, right? So what dish does in this case is that it gives the advantage of having a directional gain, right? It comes directly from the fact that the resolution here, that it has a resolution of lambda by d, d being the size of the aperture and lambda is the wavelength at which I am observing. So such a setup actually provides a very high angular resolving power at the same time as like a very good collecting area. Okay, so consequently, historically, if we look at over last 100 years or so, there have been huge efforts to build larger and larger single dish telescopes, right? Why larger and larger? Because the larger the dish, more photons you will collect, and also the more directivity you will have, right? So this is the point where these two things become sort of closely interlinked, right? This lambda by d factor. So let's look at some of the prominent single dish telescopes that we have. We have Parkes telescope. It's not a new telescope. It's a diameter 64 meter. It's situated in Australia. Then one has Green Bank telescope. It's situated in West Virginia, USA, and it has a diameter of 100 meter. So this is the largest steerable dish that exists. And more than that, it becomes increasingly more difficult to build dishes which can withhold and withstand their weight, right? It's you can see that like these are very big structures that we're talking about, and a telescope, when it sort of we steer it to map different parts of the sky, it should be able to withstand its own weight. And as we make larger and larger dishes, from engineering perspective, it becomes very difficult to do that. But people have gone ahead and built dishes which are sizes of 300 meter and even 500 meter. For 500 meter, you can look at FAST, which is 500 meter aperture spherical telescope in China. It has become recently operational, and a very famous ISSAA observatory has a telescope which was an aperture of 300 meters. Sadly, very recently it was damaged and got it's no longer operational, but for a very long time it has been the largest, not steerable, but the largest single dish telescope, and it has made a lot of fundamental discoveries. Some of the pulsar discoveries, or the more recent one that we were talking about yesterday, related to binary pulsars, millisecond pulsars, a lot of those things have been detected using actually RSCAA telescope, right? So it has contributed a lot to our understanding of the universe. So next, with this basic idea of like what an antenna is and what it should be for it to be like very useful for us to do astronomy, let's now look at what is it, how we can understand a telescope response and its imaging properties better. And for that, let's do a little bit of Fourier optics in this case, right? So what we did up to this point, when I showed you this diagram, we were visualizing this response in terms of ray optics, right? This is the fundamental role played by parabolic reflector. But now, if we really want to understand the quality of the image that it will produce, we have to do a little bit more. And that little bit more is actually very, very interesting, right? Here again, like I will start with something which I'm sure you would have already done. You may have slightly forgotten. That's always a possibility if you have not done a revision or we haven't had a chance to use it again. But that's something you would have done as part of your undergrad wave optics course, and that is like some aspects of Fraunhofer diffraction. So what we want to do here, like think of it like there is an advancing plane wavefront, right? Plane wavefront, and it is intercepted by an aperture, right? And that aperture can be a circular aperture, it could be just a slit. The question that we are asking is that what would happen, right? So just from simple wave optics, we know that what would happen as long as this interaction takes place, that every point on the wavefront can be regarded as a source of secondary wavelets. And what would happen that due to diffraction, these wavefronts would spread into the region that would otherwise be unlimited, right? If I have an aperture, and if I think of just ray optics, then outside the aperture, it's just completely blocked, right? Nothing should happen after that. But that's not what what happens when we understand that how diffraction operates, and what happens that on screen the secondary wavefronts would actually interfere, and depending on what is the path difference between them, they would interfere constructively or destructively, and this would lead to an interference pattern or the fringes that we would see. So it is this interaction between the incident wave and the aperture that determines the resolution of the optical device, right? And the kind of image contrast that I will have in my image, right? So when viewed like this, we can show that far field, and that's a very important point. The far field or the Fraunhofer diffraction pattern is the Fourier transform of the field across the aperture which is causing the diffraction, right? So that's something I will repeat it again. That the far field pattern is the Fourier transform of the field across the aperture. Right? So just hold this in your mind, and we will see what it actually means in next few slides, and we will have a bit of a fun with different kinds of aperture when we do this, right? So but before that, let's just look at a little bit of this formal description here, where we are looking at an aperture which has a constant extent perpendicular to the slide. So along this direction, let's think of it that it has an extent of A. And then what we are interested in is that to see what its response will be at a point here, right? That's what we are interested in. So now, without any sort of compromise with the generality here, what we can write here is that the field component along X due to any infinitesimal element here, dE, can be written like this, right? And since we know that electric field at a certain point here, which is at a distance r from the origin of the aperture, this can be a superposition of all the fields produced by these different elements here of this aperture. Then we can, all we need to do is to integrate over this here, right? And if we do just simple substitutions here, what we can show straight away very easily is that this E, the field here, is related like this. What is this? This is nothing but actually the simple Fourier transform expression, right? So now I have a slide or two just to remind you about what Fourier transforms are, so that we can clearly see that how they are related, right? But this is, you have to believe me at this point, in case you are not completely familiar with the Fourier transform right now, or the memory is blurred, that this is what it is. But let's look at this. So how we are generally introduced to Fourier transforms is that we are generally motivated as an extension of the Fourier series, right? And what we do is in Fourier series is that when we take some complicated but periodic functions, we can write them as a summation of simple sines and cosines, right? That's what our Fourier series expansion tells us, right? That you can have these different functions, and you can write these as summations of sines and cosines, right? So Fourier decomposition of a square wave, for example, right? You can see that this square wave, as I add more and more sines and cosines, it becomes a more and more accurate representation of this square wave. That's the idea demonstrated here in the diagram here. So now, as an extension of this, what happens that Fourier transform, we get Fourier transform when the period of the function that we are representing here is lengthened and is allowed to approach infinity. Then, this summation, I get this integral here, right? So now you can see that what we were talking about here is actually indeed true. What I am going to do here is that again now take an aperture here, which is shown here. It's illuminated by wavefront from the left, right? You can see this dimension d. Okay. So now I can estimate. This is the Fourier transform expression. So I can represent field like this, right? So it is it has a certain value within the aperture, but outside it is 0. And if I do this, make this substitution and integrate, then I find that I get this expression. This is nothing but a sinc function. So what this is telling me, the diffraction pattern of an uniformly illuminated aperture is a sinc function. This is not sine, it should be sinc function, right? So this is how it is, and that's something which we know, right? So, and this is how it happens or comes out, right? And very easily through your if you apply some simple Fourier optics. So to have a little bit more fun, if you want to sort of be nimble-footed, then it is very important for you to keep in mind some of the simple Fourier transform theorems. Let's start with a few of them. For example, you can talk about linearity. What linearity means that if we add two functions, then the Fourier transform of the resulting function is simply the sum of the individual Fourier transform. We can talk about similarity, for example, where if a function fx has a Fourier transform fs, then Fourier transform of ax would be actually 1 by a f s a, right? 1 by a. So this is something which we would have done in quantum mechanics also, because what it is telling us is that a wide function in the time domain is a narrow function in the frequency domain, right? This is pretty much the basis of my uncertainty principle in quantum mechanics. And in case of astronomy principle that we are talking about, it just means that a larger the aperture, the narrower the response will be, so better resolution it will provide you, right? Likewise, we can have shifting theorem, convolution theorem. I'll talk a little bit more about convolution theorem in the next slide. But what basically this means that if I have two functions f and g, and if I take a so these are some of those theorems that we were talking about, and then and last one is the Fourier convolution here. So if this symbol here represents, let's say, the convolution, then what convolution theorem tells me that if f and g are two functions with convolution represented by this, then the Fourier transform of the convolution of two signals is the pointwise product of their Fourier transform, right? So this is and this is a very important operation in astronomy, right? Observational data. So what this encapsulates or represents, convolution theorem here, is that the kind of modification my data takes place when it's passed through a detector, right? That's what happens. And convolution is, of course, used in whenever I'm saying that I'm smoothing my signal or smoothing my image. So pretty much what we are doing is that we are taking a kernel or a filter and convolving it with my image. That's what we are doing. So that's why convolution function is a very important theorem to understand. So now let us see, if I know convolution theorem, and I know the response of a, let's say, single aperture here, which was in this case, right? Then how can I sort of quickly work out what would be the response of a two-slit, double slit, simple Young's double slit experiment? So let us just focus on this one, right? This represents my two slits of finite width, minus t naught minus tau to minus t naught plus tau, right? This is the extent of one, and this is the extent of the second slit. So how can I represent it using just a simple delta function and a single aperture, which will be like this? So if I have, let's say, two delta functions at minus t naught and t naught, and I have the single aperture which is centered at 0, and if I do a convolution of these, this will be what? Just a shift and multiplication, right? That's what I told you, that this is what it is, this function, right? I am shifting one function and multiplying it like this, right? So if I do that, what will happen? I will get, as a result of it, a function here, a slit sitting here, and another slit sitting here, right? So now let's look at what happens in the other domain here, right? I know from my simple theoretical construct of Young's double slit experiment that if I have two slits which are eliminated, the response is cosine. This is something which you will get if you just take these two delta functions and do a simple algebra and solve for this. You will get this function, right? This is something which you can easily work out. And for the single aperture uniformly illuminated, we have worked out here that its response will be sinc function, which is this, right? So what would the response of this, without doing any additional mathematics? I know that the response would be simply a multiplication of the Fourier transform of these, which is this, right? This cosine multiplied by this. So this is my response here. So this is in a more realistic scenario when slits of finite width are eliminated. This is what I get. Like this cosine is actually multiplied by the diffraction pattern of the single aperture, right? This is how we can understand it. So I can now make this scenario more and more complicated, and then depending on how well I understand some of these theorems and Fourier transform theorems, I can very quickly work out that this is what my response would be like. Not necessarily quantitatively, but qualitatively, I can straight away tell, right? And this is a quick summary of what is happening in case of like when a two-slit setup is eliminated here, right? That's what is happening. We have this thing, we have this cosine function, and then this is getting multiplied here. Then we are talking about intensity, so we have taken a square of it, right? That's all simply that we are talking about. And if you do the same thing, and if you do the same exercise for a circular aperture, then you can show that this maxima actually, the first nulls would actually happen at 1.22 lambda by d, and half power beamwidth is 1.02 lambda by d. This is corresponding to your circular Bessel's function, or the Aries disk that we come across when we are dealing with the circular aperture. So this is where I think some of us get often confused that we have this resolution of circular aperture as lambda by d, then where do I get 1.22 lambda by d? So this is coming from Rayleigh's criteria. In this case, what we are talking about here is that if we look at two nearby stars, right, these, and the question that we are asking is that when is that they will be resolved? That is when I can tell them that they are two and not one. And that is something we can tell when the response of one is actually the peak of one is falling on the null of the other, and that separation is 1.22 lambda by 1.22 lambda by theta right? This is why often you would see that theta is actually 1.22 lambda by d. That's where it comes from. Okay. Yeah. So this is where we can now put everything together. That's what now we are at this stage now. So this is your parabolic reflector which we were considering some time ago. We can say that this resolution is 1.22 lambda by d, and its geometric collecting area, d being the aperture, is pi by 4 d square. But provided that this dish is uniformly and completely eliminated, right? That's when this geometric area will be equal to its overall collecting area. Otherwise, it will be little less than that, and that little less than that is represented by the aperture efficiency. Okay, which is this factor. Okay. So I'm not going to talk little bit anything more about it, but the fact that it is so from this, from the considerations that we have had up to this point, we can appreciate that it is really important to design antennas very well to not only be able to collect large number of photons, but they must have a good imaging response also, right? Because if we have a response which will have very strong, powerful side lobes like this, then it is not a good thing to have, right? That would, then it will not lead to good image, because my each image of a source in the sky is actually convolved with the response of the aperture that I have, right? So if I have, let's say, two sources I'm looking at, each one of them will have a response like this, right? And that can then very easily, if you have large number of sources and many of them are strong, that can very easily overwhelm the kind of the image quality that you have, right? So you must have seen these optical images which have got these bright sources, right? And they have got these spikes centered on them, and close to them you cannot really see if there is a faint source. So all that is happening because of that. But in radio, we can take care of some of these aspects by doing what is called uh, deconvolution, and we'll talk about that tomorrow. That what is meant by deconvolution. What, in simple terms, it means that now, since I know my aperture very well, I know that it will have a response like this. So if I know if each source is going to be convolved with this response, I can do an opposite of convolution, which is deconvolution, and remove this effect from my image in an iterative manner. And through that, then I will be able to detect fainter sources in the image as well. Okay. So up to this point, we have been actually talking about what does a single parabolic reflector response would be, right? Now we want to understand that is it good enough or not, right? Because if I look at it here, what we are seeing here is the simple example of the Orion Nebula, and anybody who has a little bit of interest in looking at physical objects in the sky, this is one of the first things that we see in a constellation that is very easy to identify, and the nebula itself is very bright because it represents the nearest star forming region that we can look at. So even with simple binoculars, it is easily observable. Okay, and what is the size of it? It is the whole size of it is like about a half a degree kind of. So this is like the size of the moon that you can look at. And so what we want to do here is that, let's say, if we want to image it, make an image of it, then I can take a single dish telescope, and a simple telescope may have a field of view which may be of, let's say, a degree or something like that, right? So if I want to make an image of a very large part of the sky, then I can point telescope like this and I can make an image of that, right? So that's a possibility. So now angular size of Orion Nebula, as I was saying, is like 1 degree. It's twice the size of moon, right? Now GMRT, if we take, it's a 45-meter dish. When we were talking about another single dish, which is Parkes, it was 64 meter. The largest variable was Green Bank. It is 100 meters. So their field of view would be even smaller than this, but it has a field of view of 0.3 degrees, right? So what this means is that if I point my single dish, which is of the size of GMRT, towards this, I will just see just a single blob. But you can see the enormous amount of detail which is there. Like there are some regions where, like H2 regions, where like young stars are forming and they're ionizing neutral hydrogen around that. There are other places where the supernova are taking place, right? The old stars are dying. So there are different physical processes, different types of stars at different stages in this star forming region. So a lot of complexity involved here. But if I want to actually make sense of all of it, and I have a dish which is of the size of 45 meters or 50 meter, 100 meter even, then I cannot really resolve much of that detail, right? And this is a real image that is I'm talking about. So if one makes an image of this star forming region, this nebula using HST, you would be capturing all this detail, right? So if we want to go back to kind of things we were talking about yesterday, that we want to look at same object at different wavelengths so that we can understand what kind of physical processes that are taking place in them, right? If you want to make that complete picture, it's not enough to just to be able to look at them at different wavelengths. We should also be able to have a match spatial resolution, right? If I'm want to talk about this source, this blob here, then I must be able to resolve it at all wavelengths and separate the emission which is coming from the nearby region, right? So that is important. So you can see that if we are just relying on single dish, then it is not enough. Actually, we will not be able to do what we were talking about yesterday. Is an essential thing to be able to do if you want to do good astronomy, right? So instead, but there is a solution and a very cool solution to it, and that is called radio interferometry. And what the principle of radio interferometry is practically based on something called aperture synthesis. What this means is that I can use the principle of radio interferometry to synthesize a continuous large aperture using a pair of large number of antennas. So this is what I go back to the kind of image that I was showing yesterday for GMRT, and I started today's lecture with that there are these 30 GMRT antennas, 45 meter diameter, spread over 25 kilometer area. What we do using radio interferometry is actually to synthesize an aperture which is as large as 25 kilometer, right? So the next few slides, and I don't think we will be sort of finishing that discussion today, and it's rather better to start that discussion tomorrow itself, because tomorrow then we can completely focus on radio interferometry and imaging part to talk about how it works. And I'm going to start tomorrow with Michelson interferometer for that, because that's where the roots of all the interferometry are. Right, that's what we will start with tomorrow. So now is the time to take up some of the questions that we have. So let's go into that. So I'm going to stop sharing my screen at this point and give me a little bit of time to go to see where the chat is. So there are some, let's say, like, how do we obtain the form of PN? Yes, somebody was asking that. So that is something which we have to, there are two ways to do that. One is that we can actually, in my subsequent slides, I was showing that for a simple antenna like a dipole antenna, we can work that out mathematically. That is one way to do it. And in the real life with complex antennas, we have to actually go out and measure them using, for example, artificial sources. We can point my antenna and try to work out like what is power pattern is at different in different directions. That's the way we can do it. Explain once again what is the difference by half a second with some noise radiation can filter out from source radiation. The incoming signal is so Doppler shifted to red that it is larger wavefront than the disk we have with telescope, then how the signal can be fully recognized. So I think so there are two things to consider here. So when I make this decision that I am going to observe a certain object in the sky, right? So then I have to make two choices. Is that I'm going to look at this direction in the sky, and then at the same time also make a choice that at what frequency range I am going to observe it, right? So if I'm observing a spectral signal, then in that case I have to ensure that, for example, if I'm looking at neutral hydrogen at redshift of 0, that is a line at 1420.405 megahertz, then I must ensure that my telescope, the receivers that it has, are tuned such that the signal that I'm going to receive is actually contains that frequency, right? If it does not, then that signal will go out of my band, and of course I'm not going to see that line. So then there are some of these things related to mathematics. What I'm going to do is I'm going to again share my screen and show you some of the, so this is where, right, let me share it again. Right, so these are some of the, if you have, you can already take a screenshot of this, and so if you want to have a little bit more on Fourier transforms, you can look at it. If you want to have more on specifically about radio astronomy, radio interferometry, and we will talk about it more tomorrow. So these two books like Thomson, Moran, and Swenson, and Synthesis Imaging Radio Astronomy will be more relevant after tomorrow's lecture. But no problem, you can go ahead and look at that. And similarly for principles of optics, we will also talk about something called Van-Sitter-Zernike theorem tomorrow. And that's something which you can look at in Born and Wolf because it has very well developed in optics books, and this is a very good book for that. And some of the things that we were talking about related to detector and a dipole antenna, Johnson's noise, some of those things, if you want to look at, you can look at this book by Rawls, Tools of Radio Astronomy. You will also be able to find some of the associated algebra and things in more detail there, right? So that would help. So now we have some raised hands, and let us go to them one by one. Okay. That is Sachin Dubey. Yes, please.
Yeah, thank you, sir. So my question is like when we use the GMRT, it's a like single radio telescope. So why don't we use a large number of tiny like small dishes like we have in our houses for like satellite communications? So why don't we use a large number of tiny satellite? My question is that.
Okay, so some of this thing will become little more apparent as we talk about interferometry tomorrow. But what happens that so the single aperture that we will use, right? It will have a field of view corresponding to lambda by d, d being the size of the aperture, right? So if I take a smaller aperture, then it would actually be able to see larger portion of the sky. That is a good thing, so not a problem. But at the same time, I will also the size of the aperture also corresponds to the number of photons that it will collect. That is the sensitivity part of it, right? So when people design antennas or radio interferometer, they have to consider two aspects. One aspect is that what is the size of the aperture that I should take so that like it will have a good gain, right? And second thing is that depending on what is the kind of area that I want to cover, because that's eventually the size of aperture that would correspond to, right? In the aperture synthesis, like whether it is 10 kilometers or 25 kilometers or 30 kilometers. And to be able to cover that, it is very important radio interferometry to be able to cover that area very well. You can think of it this way, like if I don't cover it very well, then I will be synthesizing an aperture which has very big holes, right? Think of it as a lens which has like very big holes in it. So my imaging response will be poor, even though my resolution will be still corresponding to the size of the aperture, right? So we have to also not only think about what is the size of one aperture, but how many of them to use so that we can fill this plane very well. And that actually represents the kind of structures we can map in the sky. And I will talk about it a little bit more tomorrow. But that's the basic idea actually, that why we do 45 meter or sometimes 12 meter or 50 meter. So you will come across different radio interferometers. They have not 45 meter, but they have like say 25 meter or 13.5 meter dish, right? And different sizes of them and different, and they can be moved around also. Let's talk about more of this tomorrow. Okay?
Okay, thank you, sir.
So next is Anushka.
Yes, hello sir.
Hello.
Am I audible?
Yes.
So in slide number 43, where we concluded all the mathematical formulation that we obtained from Fourier Transform, in that diagram of antenna, one additional red bold line could be seen passing through the focus, which was inclined to the incoming light plane. So yes. What does that red line signifies?
Okay. That's actually a very interesting thing to be able to appreciate straight away. Let me share my screen again. And so this is the red line that you're talking about, right?
Yes, exactly.
So there is an incoming wavefront, let's say from zenith here, right? And that would just be converted into a spherical wavefront and will be collected at the focus here. That is obvious to us, right? So now what will happen to this red one? Red one will also be converted into a spherical wavefront, right? but it will be focused at, let's say, at a point here. Are you able to see my cursor here?
Yes,
right.
Sir.
So at a slightly different point, but I will not be collecting that radiation because I don't have a detector sitting there. Okay. So if I can by some means also put a detector here, then I will be looking at that part of the sky also and collecting signal from that. So what I can do is that I can, for example, connect this to a receiver chain, and let's say think of it just, let's say, CCD, and this part is also connected to a CCD here. Then I will get two different images of the different portions of the sky, right? And in fact, radio telescopes, people do what is called make what is called a focal plane array, right? So which is not just one detector at the focal point, but it's an array of dipoles sitting at the focal point, and using that you can then look at a larger portion of the sky, right? Because this is corresponding to a certain response in the sky, right? But this inclined right front is corresponding to a different part of the sky. So by using that focal plane array, you can actually look at a larger portion of the sky simultaneously. So if when we were talking about this, if you have, so each one of these circles you can look at. So if this one was corresponding to the incident wavefront, let us say, you can think of these other ones corresponding to the other wavefronts. And if I could detect them, then I can actually look at this entire thing in one single shot, right? So that way, what is called is like the survey speed of my telescope is increased. I can look at map larger portions of the sky much faster, much better. That's what would happen to that red wavefront. Is that fine?
Yes. Okay. Thank you, sir.
Okay. So there is. So Sachin, do you still have a question? Okay, you have. So I think we don't have any more questions now. But let me. Okay, there's a few more things which have appeared in the chat here, and we have a couple of minutes, so there is no need to lose that time. Does those radio dishes do multi-wavelength observations, or do they probe only a single wavelength? So often these dishes actually can operate at a very broad frequency range. For example, if you talk about GMRT, and it's actually not even made of a solid surface, you would find that like its surface is actually a mesh, right? And but to the radiation that it is coming, which is at 21 centimeter or longer, this mesh actually looks like a solid surface to that, right? Because the wavelengths are that we're talking about are longer. So it can operate from starting from 1420 megahertz up to 100 megahertz approximately, right? So that's the length it can, wavelength range it can cover. Then there are telescopes like VLA, for example. They can operate from low frequencies like GMRT and up to approximately 50 gigahertz. But you will find that then their surface, since they are operating at much higher frequency, the surface is actually not like a mesh as it used in GMRT, but it's a solid surface, right? And so what happens that at the more higher frequencies that you want to observe, the more stringent requirement it puts on the surface accuracy of your reflector, right? It has to be smooth to that accuracy. And if you go back to my presentation, you will find that I have talked about this accuracy in one of the slides, but I did not sort of went into the details of it today, but it is there on my slide, and the references that I have given, you can find more details of it, and you can look at what is called Rule's formula, right? That will tell you more about it in this context, like how to quantitatively understand that how good an aperture should be for observing at a certain frequency range, right? So just talking about the aperture, the simple answer is that no, they observe using given an aperture, we can cover a very large frequency range, but that aperture then also has to be supported by receivers and backend electronics that can deal with the signal coming at that frequency. Once that is there, then yeah, most of the telescopes actually observe at a very large frequency range. Both. Actually, does the focal length of the dishes play a role in resolution or quality of the image? Simple answer is both. Okay, so no more question. I don't see any more raised hands, and we are also a bit past 11. So let's meet tomorrow. Okay, thanks a lot.